So minus nu plus p factorials, is easy, you represent in terms of gamma function. So it's really nu plus p factorial, okay, means in general it is like this, but you write it in terms of gamma function to represent negative factorials. Okay, p equal to p going from 0 to infinity. This is what we had done last time, right? This is the solution of the Bessel differential equation, which is what, x squared. So basically this has to satisfy, let me first write down what. Then when you have the equation of this form, this is one solution, and nu is not an integer, j of minus nu x is another solution. So you have to just put u to minus nu and get another solution, right? Okay, and we also saw that if nu is an integer, we also have j of negative minus nx is minus 1 for n j sub nx. This is what I have proved starting from the definition of Bessel. So that's what we have done. So to understand what this is, right? I mean, this is a differential equation and this is a solution. Let's sort of look at a few things before, what is j naught x look like, j1 x, or if nu was a j half x, what would they look like, right? Should we just start with j half and then we come to this? All I have to do is put nu equal to half, right? Or x over 2 nu. Sorry, it's a 2 also. Okay. X over 2 nu plus 2p, right? It's there. I mean, there's a 2 factor. 2 over nu plus 2p is also there. And then nu plus p factorial, which was already. I forgot this 2. All right, so that is the definition of, and as I said, nu plus p factorial, we write it as gamma of nu plus p plus 1, especially when nu is negative or something, right? But if I have to calculate j of minus half x, we need to calculate the gamma function. All right, so this is what it is. So j half would be p plus half factorial x over 2. Nu is the one which is half plus 2. Okay, so since I want to get this, all I've done is at this point substitute for nu, right? All right, so let's start looking at this. It looks Patanjali, but it will become pretty compact function. Okay. So this is an infinite series. Let's start looking at them term by term. P equal to 0, what, 1, a negative 1, something to power 1. Always negative if it is 1. So this is nothing but first term will be what? 1 over half factorial x over 2 p equal to 0, right? So this will be my first term corresponding to p equal to 0. Let's take a couple of terms. Next term for p equal to 1 to be 1, right? 1 factorial. And the next one is 3 half factorial p plus 1. Okay? X over 2. This is for p equal to 1, right? So this is what? 5 over half, right? Is it 5 halves? And the next term would be what? Positive, right? Next term would be positive, and thus p equal to 2, so 2 factorial p is equal to 2. 2 plus half is 5 half factorial. X over 2, I'm just going like this, plus, this is p equal to 4, so it is 4, right? And this is p equal to 1, so this is 1 plus 1 half plus 2. I'm just going to write it because I want to factorize that, okay, factor. So this is corresponding to p equal to 2, and so this looks like an infinite series, and it's 1. Okay, done nothing but substitute for p equal to 0, p equal to 2. There's an infinite series, and I'm trying to see if I can identify this infinite series to some function. And so far, everything's fine? Okay. So what do we know about half factorial? Now, this is where we did the gamma function last time, right? So we have to now make use of whatever we learned last time to get all these things, right? What is half factorial? Or what did we say? In order to get, what are the properties of gamma function we learned last time? There were 3 properties we learned, right? What did I say? Gamma of nu plus 1?
Gamma mu plus 1 is equal to mu plus 1 plus, or times gamma of nu.
So let's get all the properties. Gamma of nu plus 1, this is one property, right? The other property that we know is nu gamma of nu, right? That is number 1, right? So in order to use, this is the recursion, and then in order to use all these expressions, we need to have a starting point, right? So the starting point was what? Gamma of half for fractional factorials. What was gamma of half?
Square root of pi.
Square root of pi. Alright. Alright, this is what we had proved. It came from the definition 0 to infinity exponential of minus t minus 1, and we put all that stuff, right? And that was the definition of gamma function, right? So this was the definition. Right, that was the definition of gamma function, and we proved all these things last time. Now, what is half factorial? We need to calculate half factorial for here, right? What is half factorial? So in order to calculate any fractional, all I need to do is gamma of half equals square root of pi. Those properties, I can calculate anything.
Square root over 2. Is it square root over 2?
Square root?
Pi over 2.
Yeah.
I mean, okay, let's
Yeah, I
get-
don't know why I didn't
Yeah.
say pi.
Yeah,
That's what I
half
meant.
factor. You have to look at this, right? Half factor is same as gamma of this, right? Which is gamma of 3 halves. Gamma of 3, if this is the thing, which is also nothing but half of, based on this property, is nothing but half of gamma of half. Right? And gamma of half is square root of pi. So half factorial is nothing but half times square root of pi. Right? Alright, so let's substitute for that. And what about 3 half factorial? What is that? call it as gamma of phi first? Phi half, I mean, right? Which is, that definition gamma of 3 half plus 1, right, that's what it is. Which is nothing but 3 halves times gamma of 3 halves, right? And what is gamma of 3 halves? Gamma of 3 halves is nothing but gamma of half plus 1, right? Which is nothing but 3 halves, half, gamma of half, which is nothing but square root of pi, 3/4 of square root of pi. So all you have to know is only those properties. I mean, so I can write this as 3 square root of pi over 4. So tell me what is 5 half factorial now? And gamma of, so this is what we have calculated, which is 5 halves, gamma of 5 halves, okay, which is 5 halves, gamma of 5 halves is what? We just got it, right? Which is nothing but 3 over 4, okay, 3 times 5 over, I'm just writing it at this point because that is a part expression. I'm not, this is what I have. Because I need to see what happens to this whole series. Alright, so you just have to start plugging in all these things. Two fives, get 3 square root of pi. Times 4. I need to see how this is going to. So this is common, right? And let me just 2 over square root. If I just take 2 over square root of pi x to the power of half as common, x over 2 square root of that. If this is taken out, then what do I have? I have 2 over square root of pi here, looks like. Right. I do have what it looks like, I have 2 over 3, it looks like it. I have an x squared over 2 squared. Okay. Plus, I'm taking, let's say, these as common, right? 2 over square and x to the power of half has come out. So I have 1 over 2 factorial at this point. I have a 4 in the numerator, 5 times 3 I have. I take that, yeah, 2 over pi I have to count, right? So this is nothing but x over 2 or 4, okay, which I can simplify further because this is x to the power 4 over 2 to the power 4. Okay, which is 2 squared, 2 squared, 4 and 4 can be cancelled. So this looks like x to the power 4 over 5, 3, 4, 2, like a 5 factorial, okay? That's what I seems to be having. Just, so let me write this as 3 times 2, which is 3 factorial, okay? This looks like 3 times 2, and this is 5, 3, 4, 2, so it's 5 factorial. This whole thing is nothing but x to the power 4 over 5 factorial, okay? So what I have is a series. You can start looking at this. J half x looks like the following: 2 over square root of pi, x over 2, this, okay? I have 1 minus x squared over 3 factorial plus x to the power 4 over 5 factorial. The next term will be negative. Okay. What does this remind you of? So look, it's changing in sign, okay? So it has to be an odd function, okay? Looks like that, or at least the top, I mean, the 3 factorial, 5 factorial reminds you of something. Can you guess what that function, that infinite series, I want you to guess as a function? It's close to something, but it's not quite what you want, but you can do something to get what you want. Think of all the simple functions that you know. Just a wild guess.
So then maybe one over 1 minus x times cosine of x?
It's simpler than that. So just think of your sine of x and cosine of x first. Okay. What is sine of x? What is the infinite series expansion of sine of x? Sine of x at x equal to 0 is 0, at least we know that, right? So the first term of sine of x is what? It's
0.
0. So what should, so sine of x at x equal to 0 is 0. So sine of x, the leading term is what?
0.
Leading term? So the way to remember all these things, sine of x is an odd function, right? That we know. And we also know at x equal to 0, it has to be 0, right? That also we know. So it's an infinite series in x, which has to become 0. I mean, 0 is just an obvious thing, right? But x, it's a function of x, right? So what should be the first term? I mean, that's an easy, this is how you should, think about it, right? Otherwise, it's an odd function. It's an infinite series. So, these are simple trigonometry, sine and cosine. You should know how to write it infinite series and back, right? To identify series to that. So, this is x, right? Then x equal to 0 is 0, right? And all of them will have some x, right? It's not sloping series. Alternate terms are positive and negative. Okay. It's still not what I have, but it has some features I have, right? I mean, 3 factorial is there, this is there. So what should I do to this function to get that in another infinite series?
Factor out
Divided by x, right? So basically this whole infinite series is nothing but sine of x over x. So you have to remember 2 things. Cosine of x at x equal to 0 is what? 1, right? So there the leading term is 1. And what? It is a even function x. So I should have 1 minus x squared over 2 factorial plus.
So when you say leading term, you mean the first non-zero term?
First non-zero term.
Okay. When you said leading term, I thought you meant the first term, which meant the constant term, which would be 0, that's what I was saying, 0.
I mean, it doesn't, that doesn't mean
Yeah,
much.
so that's why I was saying 0, that's what I was
Yeah,
there.
yeah, you know, as a function, because I want an infinite series in X, right? I mean, I can put a 0, I mean, I can put a 0 here too, right? I mean, it doesn't change anything. But what we know is the properties at X equal to 0, cosine of X has to be 1. So here, you know, first term is 1, right? It's not a function of X, it's 1 minus X squared over 2 factorial and all that. Right? So this is how you go, you know. So these are simple trigonometric function, exponential of X, you should know what it is, right? I mean, and sine X, cosine X, and of course binomial theorem. So then you can get to many series you can identify as function, right? So, but you know, these are simple functions that you should identify. So this thing is nothing but sine of X over X. This whole infinite series is nothing but sine of X over X. And then we have 2 over square root of pi. And then I have square root of X, and I have a square root of 2. That's what I have. So since X is here, so I'm going to write down this as square root of 2 over pi over X sine X. Okay, so that, okay, I just combined all this X, you know, absorbed it here, and square root of 2 will cancel it. So this is what it is. So this is what J of half X is. Right? So you can, you know, write J of same procedure, J of minus half X you can calculate. All you have to know is these properties of gamma function, right? And that's it. I mean, property of gamma function, and how to live in kind of series. I mean, I don't have to calculate, I think, because we also know J of half and minus J of half have to be linearly independent, because there are two solutions. You can guess the solution. It has to be root 2 pi X over cosine of X or something like that. But because, you know that Wronskian has to be non-zero, they are linearly. So that sine X, cosine X, whatever, that is some constant somewhere. And the derivatives, right, from there you can guess. All right, so similarly, you can calculate J naught X. I mean, for the integer ones, you can calculate J naught X and J1X. Right? Just substitute in the same formula because of the function. So you just expand this, put nu equal to 0, and p equal to 0, p equal to 1, p equal to 2, how does the term look like, and then get the series. I mean, it's an oscillating function too, but I'm just going to write down, you can check. J sub 1x is an odd function. So this is more like it's not cosine, but it's like cosine function because it starts with a 1, right? It's even in even power of x. Except here it is not 2 factorial and all. But you can see it's an oscillating function, with some property like cosine function. this one is almost like a sine function because it starts with the x. All I've done is put nu equal to 0, nu equal to 1, and looked at a couple of terms in the p to do all that. And we know it has to be an oscillating function because it's solution of the Helmholtz equation, right? I mean, if it's a cylindrical drum, you'll have oscillating solutions in the part of that. So we also know how that then look like. So J, if you plot it, this is J of 0, x as a function of x. It'll be some oscillating function with some zeros at some point. And J1 of x is also an oscillating function with starting at 0, though, I mean, okay, something of that nature. Okay. So just as we had P naught x, was, the value P1x was linear, P2x was quadratic. So the nature of whatever, I mean, you can have J sub nx, I mean, just plotting only two of them, you can see how these functions are. And the behavior is what will dictate your wave function or what solution of your wave of your partial differential equation. So that's how these solutions look like. They look like how they look complicated, but if you plot it, I mean, this is how it's going to look like. All right, as usual, we need to know, how to calculate higher order Bessel function, like higher order Legendre polynomials, like a wave function excited state or something. We need to, have higher order polynomials because they are going to be part of your solution, right? So we have similarly a generating function method, just as we had for Legendre polynomials, a function of two variables. Which produces some function which has been, concocted or cleverly designed so that it produces a series this is a function, this is your generating function for Bessel function, and it produces infinite series. A function can be converted into a well-behaved function can be converted into a series, and with some coefficient, this coefficient turns out to be Bessel function, right? Except here the infinite series, because we know it can be negative and positive, it goes from negative infinity to plus infinity. In Legendre polynomial, what? It was 1 minus 2xt plus t squared, negative square root of that was Pnx, t to the power n, and going from 0 to infinity, right? Whereas here, it goes from minus infinity to plus infinity, because we do have j of minus n and stuff like that. All right. So this happens to be the generating function for Bessel function. So knowing basically one of the things, knowing J0 x or J1 x, how to calculate J2x, we need, what is J2x. If you want to find out, we can use generating function method. Way to do is there are two variables, so we just start playing partial of g with respect to x. We can take partial of g with respect to t. We can take. These are the only two things we can do. So if you take partial of g with respect to the function of two variables, with respect to t, so my left-hand side would be what? X over 2, 1 plus 1 over t squared exponential of x over 2 t minus 1 over t is nothing but, we are doing with respect to t, right? So j sub n x, n to the power of n minus 1, n going from negative infinity to plus infinity. And what is this quantity?
G of x t.
This one, right? I mean, yeah, so that's the one which is producing that. So I can write this, it's a generating function basically for a Bessel function. So I can write this as j sub nx, t to the power of n going from minus infinity to plus infinity, x over 2, 1 plus 1 over t squared is n. Alright, in order to get, or to compare the same power of t in both sides, right? I got x, this is multiplying the whole thing, okay? And so there are two terms here. So what do you have? First term will be x over 2. Summation j sub nx, t to the power of n. I'm just going to put summation, you know what it is. So that's one term plus x over 2. I don't want to miss that. Summation j sub nx, t to the power of n minus 2 is equal to summation n j sub nx, t to the power of n minus 1. Summation over n. All right. So if you compare the coefficient of what do you get? What is the relationship I can get? Because for the same power t, both sides have to be the same, right? I mean, this is an infinite series, that's an infinite series, each term you're comparing. So, I mean, I can choose anything, but if I chose t to the power of n, first term will be what? X over 2, right? J sub nx. What about that term? So, want to look at n t to the power of n term, n has to go to n plus 2, right? So this will be j of n plus 2x. Okay, then you'll have n going to n plus 2, you'll have t to the power of n. This is equal to, and here n should be going to n plus 1. I'm looking at one term, right? N plus 1, j of n plus 1 x. And, so just take n to n minus 1 so that I could have looked at a different terms to look at maybe neat, but we can also do here. N going to n minus 1 is will be j of n plus 1 x. J of x. So we have the first relationship or identity, which is a recursion relation, in this case, for Bessel function. What it says is j of n minus 1x plus j of n plus 1x is nothing but 2n over x j sub x. So knowing J0, put n equal to 1. So this is a J0, that's J1, you can get J2. Okay, so that's a recursion relationship. So what do you get by taking partial G with respect to X? There are only two manipulations that we have here. What identity do you get? So what do we get? The first term here. This is just a definition, right? So we are only differentiating, taking a partial with respect to X of this term and that term.
1/2. And then you can E the X over 2, E the other, it's equal to J prime of n.
So can I write this as summation? I mean, now do you understand, can I already start writing like this? Right, because I get that, which is same as my definition of Bessel function, right? And then my right hand side is J prime nx T to the power n summation n going from minus infinity to plus infinity.
Shouldn't that be T minus 1 over 2?
What happened?
1/2 T minus 1 over
Oh, 1 over t, yeah, of course. It's a 0 otherwise. Yeah. Okay, so this times the exponential, and the exponential is same as that, so I just skipped one step, because you already now know, and this is the derivative right here. Alright, so because I got t and everything, so I need to take the t inside the summation to compare, say, powers, right? So we will have, let me take the 2 there, I mean, maybe, so I can have j sub nx, t to the power n plus 1, summation n, minus summation of j of nx, t to the power n minus 1, n. This 2, let me take it there, okay, is 2 times j prime nx, t to the power n, going from negative infinity to plus infinity. Okay, so which we want to compare the power Tn, maybe, right? Then if you did that, then we are looking at j of n minus 1 x minus here then n plus 1 x, right, is equal to 2 times j prime of nx. So that gives you an under identity. So let me call this recursion relationship as identity number 1. Okay. We got this by taking partial of g with respect to t, and this one we got by taking partial of g with respect to x. Right. So I'm going to write 2 more identities, and I'll prove identity number 3, 4 by extension, if you can get it. Okay. Okay, derivative of x of n, j, and x is this, okay? And identity number 4, I'm going to write, but I'm going to only prove identity number 3 because it comes automatically from the other one. Once you know the property of one, we can do the same procedure. Okay, so I'll prove this. The goal of all these relationships is to prove that whatever the coefficient was of the generating function is your Bessel function. Otherwise, it could be any coefficient. Otherwise, what does it mean? I mean, you know, you have a function, you put it in an infinite series with some coefficient, whatever you could call a and b and c, and doesn't matter. And then whatever a and b and c and or x is nothing but Bessel differential, Bessel function. So all these equations should result in what? I mean, we manipulate and, you know, basically say this, right? Yes, this is a solution of a Bessel differential equation, so that should satisfy whatever the coefficient is, I mean, right, should satisfy this differential equation. So it's a bit easier than, you know, the Jean Paul, because already, you know, all these things are derivatives out there and all that, and so one can, you know, convince ourselves. Okay, let's see proof of that, which is completely different. We start from the definition and prove it. Right, so I'm going to erase this because I'm going to prove that. I'm just going to put, I got x nu here. Supposing I want to prove, since I wrote it like that, I need to prove d over dx of x nu j nu x. Alright, so I have this. This is a definition of Bessel function, okay, with me and that. So I want to multiply by x nu and then take the derivative. I mean, that's the simplest thing I can do, right? I don't know anything, that's all I'm going to do. Look at that. Summation is over p, so I can put the x nu inside. Alright, so this is nothing but summation p going from 0 to infinity of minus 1 for p. P factorial, u plus p factorial, okay. And I have got what, okay, let me just separate out. This is x nu, this is 2 to the power of mu plus 2p, and I have mu plus 2p, and that mu, alright. All I've done is absorb this x nu to the numerator, and separated this one because that has got a different exponent at this point. This is 2 to the power of mu plus 2p, right? That is x to the power of mu plus 2p. Then I multiply by x nu, so I just absorb that in the numerator. Right. That's all I've done. Now, you know, these are simple functions, and I have to take the derivative of that and see what happens. All these things are constant. The only thing is this, right? So it's fairly simple to calculate. Okay, x to the power of n kind of a thing, constant, right? So what is that? N x to mu to p minus 1. I can write it like that, right? This is 2 times mu plus p, right? This can be written as 2 times mu plus p. I just put that so you see what I've done. So this is nothing but 2 times nu plus p. I have a nu plus p factorial here. Can I write the denominator as nu plus p minus 1 factorial, because that is nothing but nu plus p times nu plus p minus factorial, right? And nu plus p will cancel that. And I can write this as what? 2 nu plus 2p minus 1. Okay. So this whole expression can be written as follows. Summation p when 0 to infinity minus 1 of p factorial, and because of that I can write this as nu plus p minus 1 factorial, okay, and because of this too I can write the denominator as 1 over 2 u plus 2p minus 1, and then my x is now would write this as x nu plus 2p minus 1, right? This is 2 nu, right? So I can write it like this, right? So what I have is then, that's the summation is over p, so I can write this expression as nothing but x nu times this, all this stuff. Right? So what is that? This is my definition of, all I've done is here, what we have is nu has become nu minus 1, right? Nu has become nu minus 1, the rest is the same. So what can we call that as? So here, let's get
So we get u minus 1.
1x, okay? So that's what that's. So this derivative is what we want to do, right? So all we just took the definition, multiplied the x nu, right? And took the derivative with respect to x. X is there only here, so that all this is really a constant, so this is what you have to differentiate with, right? And then I just, I know what j minus nu and x looks like, so, this I factored out, so that this looks like x over 2, nu plus 2p minus 1. So that's it, so it's fairly straightforward, proof. Although it looked, so you can see all these identities are fairly simple, although the Bessel function looked pretty messy stuff. These relationships are fairly simple, fairly elegant proof, and from there you can, you have all this expression, you can take the derivative and then do j, you have to somehow get j double prime and x and manipulate it and get it, okay? So you can, that's how you convince yourself that whatever happened in that generating function, that coefficient is your Bessel function. We generate some identities, and two identities we get by partial g with respect to x, partial g with respect to t, and we need sometimes more than, in this case, we generated something which is fairly simple. Okay, yeah. So I'm not going to prove that, but you can convince yourself. We did it for what is it called? Legendre polynomial, right? Yeah. What's happening here? let's now go to the integral representation of the Bessel function. We had what in the, for Lejeune polynomial, we had a differential representation, Rodriguez formula, right? I mean, we had. So here, actually fairly, it's a very elegant proof of, and you'll see this representation in optics quite a bit, especially drawn after a diffraction through a circular aperture or something. You see these kind of forms of Bessel function. What we have just seen is many of the properties eventually will come out of the generating function representation, right? Generating function. Right? This is what we just saw. That this is a function which generates the Bessel function. In this, just try to put t here at exponential I theta. Make this substitution. What happens to my left-hand side? Write this. So what is my left hand side? This one. What is exponential I theta? Can I write like that? So if I subtract this out of, or from there, so this is nothing but 2i sin theta, right? And there's a 2 here, so I can write this exponential ix sin theta is equal to summation j sub nx, and going from negative infinity to plus infinity of exponential I n. So all we have done is the substitution in this generating function. All right. So I have some function here and I've got some infinite series here. So can we write my left-hand side? What can I write my left-hand side as? If you want to expand that as by term, what is my left-hand side? The series is going from minus infinity to plus infinity.
Should we still have a x over 2?
X over 2? No.
Each
Here?
x over 2?
I have an x here, right? This is what you're asking?
Yes.
Okay. So what I did was, this divided by 2 is what? I
I see
sin
what you
theta,
did.
right? And x. So I've written that as that. So x, so that x is there, but got there, but 2 got cancelled. Okay. All right. What is my right hand side? Yeah.
Plus n theta plus I sin theta. Summation of j of n with cosine of
And theta, I said
theta.
theta. Yeah, that's okay. But I want to do it term by term. Look at this, okay? See, yeah, that's okay, fine. But what I want to look at is this infinite term. I'm going to what I need is the following. Somehow, I have to get a representation for Bessel function in terms of some integral. That's by integral representation. That's what I need, right? I somehow have to extract out the j and x from this infinite series. Okay? I mean, I will have to eliminate a lot of terms and all that thing. But I want you to separate out n equal to 0, n equal to 1, even and odd terms. There is a property. What did we talk about j of minus nx? Because they're going to be, you know, if you expand this, you've got term j0x, j1x, j2x. You also have j minus 1x, j2, j minus 2x and all that. Okay? So can we split this infinite series into some odd terms and even powers of n and see what happens to it? I mean, just expand and let's see what happens, right? N equal to 0, this is 0, right? And so I do have that term, right? And then you do have the one which you were saying, j1x, I theta I have n equal to 1. But I also have n equal to negative 1, right? So I'm going to combine these terms, n equal to minus 1, I got terms like this, okay? I got terms like this. Right? I got odd terms. So, you know, all the odd terms we can combine in one way. Okay? So that is your infinite series, and let's start seeing what happens to this. Okay. So this is where I want you to use the property we learned last time. What did we learn? J of minus nx is negative 1 of n, j sub nx. You remember this property that we learned last time? Okay. So n equal to 1 here. So this one is minus of j1x exponential minus theta. Okay. And so all of them, these things will have minus j3x and all that, and I can pull up. Whereas these will be positive. So when you combine the exponentials, some of them will become cosine, some of them will become sine term. So let us start separating them out. So this expression is nothing but exponential of I x sine theta is nothing but j0x. Okay. I'm going to write just I mean, what I'm using is that, right? So I can write this as j1x exponential of I theta. There will be negative sign. Okay. All right. All the odd terms will be like this. Exponential I 3 theta minus exponential negative I 3 theta. Okay. And then I have even terms, which is j2x will be exponential of, that is plus, right? Exponential of I 2 theta plus is to negative plus exponential negative 2 theta. Right? Exponential I 4 theta plus exponential negative I theta. Okay. And what is this term? Based on what we have
2i sine theta.
Yeah, so these are all 2i. So this will be what? 2i sine theta, right? And that one will be, next term will be 2i sine 3 theta. Okay, so that's how it looks like. So this will become that, plus 2i sine 3 theta. Okay, and so on and so forth, all these things. Okay. And what about these things? What will this become? If it is plus, you're adding, right? Cosine 2 theta, I sine 2 theta. So that will be 2 cosine 2 theta, right? So this will be without imagining. So this will be 2 cosine of 2 theta, right? And so this will be 2 cosine of 4 theta. Okay, so let us start looking at this. in a clean manner. So what I have is exponential of ix sine theta is j0x. Now I'm going to write it in a compact notation. Is j1x. So I can write it like this. I have a two factor, right? I can write it as now I can move 0 to infinity because I've already taken care of that. Let me just see. Can I write it like this? This is fine. I can just check it is fine. Oh, sorry. So it is sine. So again, mistake. It's already sine. Sine of 2n minus 1 theta. Okay, 2n plus 1. Okay, 2n plus 1. Because we start with j1, right? N equal to 0. Yeah. Okay. Plus 2 times n going from 0 to infinity j2nx of cosine of 2n. Right, so this is what this whole expression has become. All right. All right. Then this is I. This is I2. This is 2I something, right? So this is imaginary. All right. So what else can I do now? I got a mixture of real terms and imaginary terms. Can I write this as cosine of x sine theta plus I x sine theta? And then compare the real part with real part and imaginary part with the imaginary part. Okay. So write this as cosine of x sine theta plus I sine of x sine theta. Right? Compare the real part, imaginary part is that. Okay, real part would be this and that. Okay. So we end up with the following expression now. What I have is cosine of x sine theta is nothing but j naught x. This is the real part, right? Plus 2 times summation of j sub 2n x cosine of 2n theta, n going from 0 to infinity. The other term I have is sine of x sine theta is nothing but imaginary part, so I can forget about I. So 2 times j of 2n plus 1 x sine of 2n plus 1 theta. Is this clear what I've done up to this part?
Why did we forget about the imaginary part?
I mean, it's there, right? I mean, I is there, I is there, I and cancel. Okay. So,
Okay.
yeah. All right. Now, my goal is somehow to get some representation for this coefficient, right? So, I have got cosine. Okay, if I now multiply this by cosine of m theta and integrate between 0 to pi or 0, yeah, and let me just see, yeah. We have to see what happens to it. Let's just it's all right. multiply both sides. By cosine of m theta in the first expression, and integrate between 0 and pi. Integrate between 0 and pi. Let's see what happens there. I have 0 to pi, cosine of m theta, cosine of x sine theta, de theta, 0 to x, j naught is a constant, right? I mean, and cosine of, what is that? Yeah, j naught of x, cosine of m theta, de theta, plus 2 times plus 1, right? 2n plus 1. What's that is 2n. This is 2nx. J2nx, n going from 0 to infinity of cosine of m theta, cosine of x, sine theta, de theta, going from 0 to pi. Alright, what is this term? Something sin m theta over m or something like that, right? Sin theta. So what is sin m theta integrated between 0 and pi? Because, yeah. So the first term is 0. Okay, so I don't have contribution from there. Okay. What about this term? This looks like cosine of A times cosine of B, right? 2 cosine A, 2 is also there. Can I write it as what cos of cosine of A plus B plus cosine of A minus B kind of a thing? Separate it out. Right? It looks like this, right? Maybe I should write it like this. That is what cosine A, cosine B minus sine A, sine B. So cosine, yeah, is it plus, right? Yeah. So this is what it looks like, which will be 2 cosine A, cosine B, right? That will be 2 cosine A, cosine B. Okay, where A is m theta for you, and that is that, right? So this whole thing can be written as cosine of, there are 2 terms, right? Cosine of, doesn't matter what it is, m theta plus x sine theta, something, okay? A plus B, okay? Then you have cosine of m theta minus x sine theta. Sorry, what did I do?
Do we have cosine?
Sorry, I made a
2n
mistake. I
theta?
made it, n theta, sorry, yeah. That is, yeah, this is n theta. I multiply by that, this is cosine of 2n theta. Yeah, correct, yeah. This is what we, this is what we're doing, right? We multiply with cosine of m theta there.
And d theta.
Yeah, so this is this, okay? So it's not, it is m theta, 2n theta, okay? M theta minus 2n theta, okay? Just, that's all it is, okay? Which is 2 cosine of m theta cosine of 2n theta. All we have done is multiply by cosine m theta, okay? Cosine of m theta, yeah, both sides. This is what we multiply by. Okay. Now, this term, again, what doesn't matter m theta plus 2n theta, it's some number, so again, sine over something, so it's going to, it's not going to contribute between 0 and pi. Some integer, right, same argument. It is this term which will contribute when m is equal to 2n, otherwise which will become day theta, right, and then the only contribution to this integral comes when m is equal to 2n. So this is nothing but, otherwise that basically that is cosine of 0, so you know, which is 1, so day theta integrated with 0 and pi is pi, okay, with a 2 factor, of course, this is with a 2 cosine, right? So really, the contribution is coming from this, so integral of this term is nothing but, if you didn't have just, if you had cosine A, cosine B, then put pi over 2, but this is nothing but pi, Kronecker delta of, there's a contribution only when n is equal to 2n. This is the value of that integral, correct? Because this will not contribute when you integrate, that's a sign between 0 and pi, it will go away. This will contribute when the arguments are exactly the same. So that's what it says is, your n, this 2n, which should become the summation of all the terms in the summation, only one will survive when 2n is equal to n. So the summation will go away, and the only thing which becomes is, this whole integral is nothing but 5 times jmx, because 2n has to be equal to n, right? So this whole thing is nothing but 5 times j sub mx, right? Because of that, because the contribution is there only when m equal to n, where m is what? Even, right? Because when m is equal to odd, that is 0. Okay, there's no contribution. So we have already some integral representation, but it is only for limited thing, which is for even m. But I will generalize this further. Okay. So what I find is j of mx, based on this, is 1 over pi. Okay. 0 to pi cosine of m theta, cosine of x sine theta, d theta. Where in this, when you write it this way, m is only even. When m equal to odd, that term is 0. Okay. Is it clear? Equal to 0 in this representation, equal to 0 when m equal to odd, based on this expression. Okay, that's all it says. Now, the same argument, we have another expression here. Now you can multiply this by sine of m theta, come up with similar thing. So if you multiply this now by sine of m theta, okay, and you have sine of m theta, and integrate between the same arguments, like 0 to pi with respect to theta, okay, 0 to pi. So when you do this, now we also have that cosine of a minus b minus cosine of a plus b will be 2 sine a sine b. So similar argument, and only the term sine of a minus b will contribute. One of them will really contribute. Okay, I mean cosine of a minus b will contribute. So we have cosine of a minus b minus cosine of a plus b is what? Is 2 sine a sine b, right? Is this clear? This is cosine of cosine a cosine b plus 2 sine a sine b. That is cosine of a cosine b minus sine a sine b. Cosine will cancel, and you will have this. So you will have contribution. So when you have this, again, contribution when m is equal to odd. Okay, so your another expression, which is we had an expression for m equal to even here, right? So you will have another expression from the other one, which will say j of mx is 1 over pi, 0 to pi, you're multiplying that by sine of m theta, sine of x sine theta, j theta. Where m is odd here. Use this expression, it's equal to 0, then m equal to even. So here, what we have just used is 0 to pi sine of 2n plus 1 theta. Or we have used it's the orthogonal property of sine functions, right? That's what we used. Sine plus sine of n theta. Okay, the theta is, whatever is this integral, since I didn't put 2 there, you can write as pi over 2 delta n 2n plus 1. It survives only with these are the same. So that's the only property I've exploited. The other case I exploited the property, cosine property. And so we have got this. So I can really combine the two into one single expression, that is n is odd or even. So this is the integral representation of Bessel function. What it says is j sub m of x is nothing but, I can just add them up, because when m is equal to odd, that is 0 and this will pick up. So I have one single expression whether m is odd or even is the following. And I can even multiply by I or something, but let's do this. Cosine of m theta. So what you have is cosine of a cosine of b. That's what we would, right? Plus 1 over pi I have taken out. Sine of n theta, sine of x, sine theta, theta, right? So this expression is true for all n, right? For all n, whether it's even or odd. So that way it's one compact expression. This looks like cosine of cosine A, cosine B, cosine A, sine B. So I can write j sub mx as follows. That's your integral representation. Alright. All I've done is just added the two expression, okay? And since for m equal to odd, that doesn't contribute, this will contribute. And when m equal to even, that will contribute, the other one will be 0. So I can add up and give a single compact expression for the entire regime, okay? So I think this is what is called as integral representation, and I'm just going to write j0x. You can check j0x, which will be the Bessel function of 0th order. The representation, if you just substitute here, and maybe this is what you will see often in your optics class, in the diffraction pattern expression, intensity of the diffraction pattern, you can write it like this. I'm not going to prove this, but it is really coming from this stuff, okay? And in order to get this, I think they have put an I or something so that you can get it. You put m equal to 0 and you get it, and it's an even function, so you expand this to, you can 0 to 2 pi, and that's how you get this expression basically, okay? And sine of x sine theta is 0 basically in that regime, so you can add that to it, okay? So m equal to 0 is this, and you also know that 0 to pi sine of x sine theta is 0, right? I mean, it's an odd function, n equal to 0, what do you have? It is simply j and x is 1 over pi, 0 to pi of cosine of negative x sine theta, where cosine is all even function. So I can write it x sine theta too, no problem, right? I mean, let's minus or plus doesn't matter, right? So, and this is also what I can write it as half of 0 to 2 pi, because it's an even function. I can write it like this also, right? So add, I times this, you can add 0 to this function, or I times that, then you can get this particular expression. Okay. You have this expression, okay? And you can give it that way, no problem. The way normally we write it like this is because I can always write this expression 0 to 2 pi. It's an odd function. So this expression, okay, you can plus, you can have 1 over 2 pi if you wanted, plus I times that, if you add it, you can get this expression. All right? Is this clear? Because I can add to this something which is 0, right? I mean, I have this, something 0 I can add. Something 0 could be this, right? Because that is 0. So nobody is stopping me from adding that because it is 0. Right? But I can also put I times something 0, okay? So this is cosine theta plus I sine theta is nothing but exponential I x sine theta. Okay, so this is the general form you look at it, but if you can leave it like that, that's fine, that's perfectly all right, because this is a very general expression, n equal to 0, that's what you get. But in books you will see J0x represented like this, okay? And that's coming because of a little bit more manipulation with recognition of the facts, sine of x sine theta is 0, and if it's 0, add to that, and then put imaginary part also in front of it, doesn't matter, and then you can get this compact notation. So this is what you will see all the time in optics, in diffraction pattern. Bessel functions, the zeroth intensity of the diffraction pattern, the zeroth order, which has got the maximum intensity, will have this kind of a distribution, okay, the intensity of through some circular curvature or something like that. That's what you will see. All right, let me stop here. If you have any questions, you ask me. But so that's complete sort of Bessel function. So what we did was started with second order differential equation for Bessel, and use the for series method. You know the solution. That's how we got the series generating function method, right? Okay, the recursion relation. From there, we got the integral representation of the Bessel function, okay, which is a completely different beast in some sense, but that's a very useful one in optics. So I thought I would, show you that so that when you see it in 611 or something, you recognize that, right? I mean, even 611 will have a lot of these things. So you recognize where it comes from. Just as we saw, in electromagnetic theory, 1 over r minus r prime is written in terms of Bessel function, and here J0x is written in terms of something like this. So you start recognizing very special functions appear in physics. All right, so homework, if you have finished, please give it to me. Yeah.
With the integral representation again and again.
Everything that I've covered up to this, because next part will be talking completely different. Okay. So anything with the Bessel function, and second order, maybe you have to know how to solve power series method for second order simplification. That's all we have done, right? Johnson method, properties of the Legendre polynomial, right? All these things. So here we just started with the generating function method, and the key here is it's not the only representation, right? That substitution of t into different, you get different representation, right? So you can play with that, okay? And you can see Bessel function in different forms. And so that's what we did. We just started with that, and then all we had recognized was how to write exponential I theta or something, like cosine theta, I sine theta, and
Oh.
we got some expression and then use the, these are called Hoffman normalization problem, cosine 0 to pi, cosine n theta, cosine n theta, that survives only when m equal to n kind of a thing, and that comes from the, just separate that into cosine of a plus bn minus bn. Just, then you have one cosine function, you know how cosine function, when you integrate between 0 and pi, behaves. So just simple integrals, and then that's how we got these expressions. Alright? Okay. Yeah. Yeah. Okay, that's fine.
When will we be able to pick up these, like the graded versions of these?
The class is Thursday, right? I mean,
Yeah, that's Thursday.
what was it? Many of them are generating functions, something like that, right? Yeah, I don't know whether I can grade tonight or because I've got to go or something else.